Okay, question 15, a little bit trickier. So, at time t equals 0, a parachutist jumps out of an airplane which is travelling horizontally. The velocity vector, v meters per second, of the parachutist at time t seconds is given by v is 40 e to the minus 0.2 ti and 50 e to the minus 0.2 t minus 1 j. The unit vectors I and j are horizontal and vertical respectively. Assume that the parachutist is at the origin when t is equal to 0. Model the parachutist as a particle, and part A wants us to find an expression for the position vector of the parachutist at time t. Okay, so the position vector describes our displacement from the origin after a certain time. Displacement is the integral of velocity. So, our position vector r is the integral of 40 e to the minus 0.2 ti. So I'm going to write that as 40 times the integral of e to the minus 0.2 t with respect to t, and that is the I component, add 50 times the integral of e to the minus 0.2 t minus 1 with respect to t, and that is our j component. So, when you integrate, let's just take this up here, when we integrate e to the minus 0.2 t with respect to t, we get 1 over minus 0.2 e to the minus 0.2 t, at a constant, of course. So, we are going to get 40 times minus 1 over 0.2 e to the minus 0.2 t, add our constant, so that's our I component, and then add, well, we get 50 lots of minus 1 over 0.2 e to the minus 0.2 t minus 50t, sorry, 50 is on the outside, so just minus t for now, and then we're going to have a different constant, so we can't call this one c as well, so we'll call this one d. So that is our j component. So let's sharpen this up. 40 times minus 1 over 0.2 is minus 200 e to the minus 0.2 t. So that is, don't forget constant, that is the I component. Now, our j component is 50 times minus 1 over 0.2 is minus 250 e to the minus 0.2t, and then we get minus 50t, and then we get add the constant t. So that is our j component. So at the moment, that is our position vector. Now the question told us when t is equal to 0, the particle, the parachutist, is at the origin. So when t is equal to 0, r is equal to 0, I add 0, j, which then tells us that minus 200 e to the minus 0.2 times 0, which is 1, add c is equal to 0. So c is equal to 200, and it also tells us that so again, e to the minus 0.2 times 0 is 1, so we get minus 250. The 50t disappears, so we get minus 250, and d is 0, therefore d is 250. So finally, the position vector is equal to minus 200 e to the minus 0.2 t add 200 I add minus 250 e to the minus 0.2 t minus 50t add 250 j. Cool. All done. Okay, part B tells us the parachutist opens her chute when she has travelled 100 metres horizontally. We want to find her vertical displacement from the origin when she opens her chute. So, from knowing that she has travelled 100 metres horizontally, we can work out the time taken. So, the horizontal part of our vector is minus 200 e to the minus 0.2 t add 200. So we want then that to equal 100. So minus 200 e to the minus 0.2 t add 200 is equal to 100. Now if we add the exponential and subtract 100, we get 100 is 200 e to the minus 0.2 t. So divide by 200, we get 1/2 is equal to e to the minus 0.2 t. Take logs, log of 1/2 is equal to minus 0.2 t. Therefore, t is equal to 1 or minus 1 over 0.2 log 2, which if we go to 3 decimal places, we get 3.466 seconds. So now we know the time. We're now going to substitute that into the j part of our vector. So when t is equal to 3.466, we get we're going to get minus 250 e to the minus 0.2 t minus 50t, add 250. Now if we shove in t equals 3.466, then we will get minus 48.3 meters. The reason that is negative, of course, is because the parachutist is falling, so she's going to be under the origin. Cool. Okay, then the final part says, carefully explaining all the steps you take to deduce the value of g used in the formation of this model. So, g is gravity. Gravity is trying to push us downwards. So, in the velocity vector, we know the horizontal component and the vertical component. So we're going to consider the vertical component of v. So gravity is trying to push us downwards, our vertical component is telling us about our velocity downwards. So let's think about this then. If we think about this at the start of the jump, so when t is equal to 0, we could probably get away with assuming that the only force acting on us would be gravity. So or at least the only downward force. So at time t equals 0, we could assume the only downward or the only vertical force. So we're assuming that there's nothing pushing us back up at this point. So gravity is the only vertical force. Now, gravity is going to be accelerating us downwards. So we need to find the acceleration of the parachutist downwards. So, acceleration is dv by dt. So for us here, acceleration is going to be the derivative of 50 e to the minus 0.2 t minus 1. So this is going to be the derivative with respect to t of 50 e to the minus 0.2 t minus 50. Now that is going to give us, so the minus 0.2 comes down and multiplies 50, so we get minus 10 e to the minus 0.2 t, and that's it, that's the derivative. So at time t equals 0, we are just assuming that our acceleration is equal to gravity, which is minus 10. So gravity is trying to push us downwards, so the actual value that we are using then, because it's negative, because it's pushing us downwards, but our value of g, we are using g equals 10 meters per second squared. Cool.